In the last video, we looked at an explanation based on length contraction and time dilation for why nothing can travel faster than the speed of light. In this video, we'll look at the same thing, but we'll actually look at some of the mathematics. You're not responsible for knowing this, but it's interesting, and if you are inclined towards math, then you'll find this very enjoyable. The mathematics of special relativity was actually developed in significant part by this Dutch physicist, a fellow by the name of Hendrik Lorentz, who had speculated even before Einstein about the possibility that space can contract and time can stretch out in dealing with these equations of electromagnetism. And he had actually, purely speculatively, he didn't turn it into a whole theory, but purely speculatively, he came up with a mathematical equation or a mathematical constant, a factor, that would relate the effects of space and time at speeds relative to the speed of light. This is called the Lorentz transformation, and it looks like this. And you'll notice the symbol for it is gamma. But you'll notice that here, this part of the factor is relating the speed of an object to the speed of light. And the relationship is simply 1 minus the speed of the object divided by the speed of light. This is the fraction of the speed of light you're traveling at. If you square that, subtract it from 1 and take the square root, that's the factor that relates the effects on space and time on an object traveling at different speeds. So let me show you how this works. And explain why relativistic effects, even though they're always happening, there's always length contraction anytime two objects are moving relative to each other, there's always time dilation, but we don't notice this in our ordinary lives because we don't travel anywhere near the speed of light. So let's look, for example, at the fastest moving man-made object. Well, that's the Parker Solar Probe that was launched by NASA in 2018 to study the sun. And it moves actually a little bit faster. Its top speed has been a little bit faster than 68 kilometers per second. But let's go with 68 kilometers per second. That's the fastest moving object that has ever been created. So what's going to happen to the length of this object as it's moving relative to us at 68 kilometers per second? Well, notice in the Lorentz factor, this is the square root of 1 minus something. So this number is always going to be less than 1. Length contraction tells us the length will get smaller than it was originally. So we have to multiply it by this factor because this factor will be less than 1. So this is the equation for the length of an object traveling at a particular velocity compared to its length at rest. This L naught means the rest length. When it's stationary relative to you, this is the length when it's moving at some particular speed. Okay. So let's plug in our numbers. The Parker Solar Probe is 3 meters in length. It's traveling at 68 kilometers per second. And the speed of light, c, remember, is 300,000 kilometers per second. So if we plug that in, 68 divided by 300,000 comes out to 0.00227. We have to square that, and we get 0.00000051. Subtract that from 1, we have 0.99999995. We need to take the square root of that and multiply it by 3 meters. The square root of 0.99999995 is 0.9999975. That's awfully close to 1. We multiply that by the rest length of 3 meters of the Parker probe, and we find out that if we could measure the Parker probe as it's traveling relative to us at 68 kilometers per second, we would measure it as 2.999999992 meters long. That's a difference from the rest length of 8/100 millionths of a meter. That's nothing we're ever going to notice. That's nothing we can really measure. And so even for the fastest moving man-made object, the change in length is only 8/100 millionths of a meter. At ordinary speeds, the speed of a racing car, the speed of an airplane, the change in length, the length contraction is even smaller than this. And this is why we don't notice it at the speeds that we're familiar with. The same sort of thing happens to the change in the time on the Parker Solar Probe's clocks. So this is the time as we measure it moving relative to us. This is the time at rest. And again, now since the time is going to become greater, it's going to be dilated, this factor, the Lorentz factor that's less than 1, has to go on the bottom here, because putting a number less than 1 as a denominator is going to make this bigger. Well, if we plug these numbers in again, 68 kilometers per second and the speed of light, and we do all the calculations, we find that the change in time, that the time of the Parker Solar Probe's clocks has dilated from 1 second to 1.000000003 seconds. Again, a dilation of 3/100 millionths of a second. Nothing we're ever going to notice at our ordinary speeds that we're used to. These relativistic effects only become noticeable near the speed of light, when this fraction is going to be close to 1. So let's look at that. Why can nothing travel faster than the speed of light? We've already seen this qualitatively because at the length contracts to 0, the time dilates to infinity and therefore stops, but we can see this mathematically. At light speed, the velocity of the object is equal to the speed of light. V is equal to c. So if we take our equation for the length of the object and we plug in the speed of light as its speed, we have c over c, and c over c is equal to anything divided by itself is equal to 1. So we now have 1 minus 1 squared. 1 squared is 1. So we have the square root of 1 minus 1. 1 minus 1 is 0. The square root of 0 is 0. So the new length that we're going to have will be the rest length times 0. And anything times 0 is 0. Everything at the speed of light reduces to a length of 0. And as far as time goes, again, we have this equation for time dilation. V is going to be equal to c, so c over c is equal to 1. 1 minus 1 is equal to 0. We have a 0 in the denominator. Mathematically, we might say this is undefined. From a physics perspective, how many times can 0 go into anything? An infinite number of times. So the time at the speed of light stretches out to infinity and therefore stops.